Hi everyone, my name is Jose Emilio Muñoz. I'm a software engineer at ARM, here to talk to you about Vulkan Best Practice with a focus on mobile. Before I start, a brief introduction to ARM. ARM is the world's leading supplier of semiconductor IP. If you have a mobile device, there is a very high chance that it will be powered by ARM technology. ARM designed processors power everything from cars to smartphones to the most powerful supercomputers. ARM's GPU, Mali, is the most popular worldwide, with over 1 billion chips shipped only last year. And as part of ARM's ecosystem and engineering team, I am focused on helping developers get the most out of their Mali GPUs. When talking about graphics, the last 5 years have all been about Vulkan. I will start this presentation with a bit of background on Vulkan and some of the things that we must always keep in mind when developing for mobile platforms. Then, I will take you through a couple of examples for optimal API usage, and I will close with a collection of resources that are available to make Vulkan easier to learn and eventually to master. Let's start with what is Vulkan and what are some of the key characteristics of mobile platforms. Vulkan is a high-performance graphics and compute API for programming and controlling modern GPUs. It is a low-level API designed to expose the GPU to the application developers with a minimal level of abstraction, much closer to the underlying hardware than OpenGLES. This means that many things that were previously handled by OpenGL and OpenGLES are now the responsibility of the application. This includes GPU memory management and dependency tracking and synchronization, which we'll talk about later. Vulkan drivers do not do any error checking, so it is up to the application to ensure that all code is correct, or otherwise it will result in undefined behavior. To assist on this, there are Vulkan validation layers, which can be inserted between the application and the driver and used for debugging, and then removed before shipping the application. This enables Vulkan applications to benefit from very low CPU overhead, low memory footprint, and a high degree of performance stability. However, this also makes Vulkan complex and aimed at power users. The Vulkan community is very active and full of resources that make it much easier to learn the API and to understand its best practices. And I will take you through some of the main examples of these tools and resources at the end of the presentation. Let's now briefly talk about what are the main things that we need to consider when targeting mobile platforms. The main one is that, unlike PCs and consoles, handheld devices have no active cooling, and therefore must run at a very limited power budget. For the best user experience, applications must be efficient and not drain the device's battery, or make it get so hot that it will be uncomfortable to hold in their hands. One of the most power-hungry operations are memory accesses. So, looking at the GPU microarchitecture of these platforms, typically we will find that desktops and console GPUs use an immediate mode architecture, whereas mobile GPUs are commonly tile-based. We're going to go to describe each of these in a bit more detail, as we will be referring back to these concepts when reviewing some of the Vulkan best practices. On the one hand, we have immediate mode GPUs, which as I said are typically found in desktop and consoles. On the right-hand side, we can see an abstracted view of the hardware pipeline. The geometry input will be fetched from main memory and will be processed so that the projected triangles are added to a FIFO queue. Pixel processing is then going to go and get these triangles out and shade them, draw call by draw call. The color and depth frame buffers are large and need to be stored in main memory, so that each draw call can access the most up-to-date data. This gives us less expensive triangles, since their transform data can stay in GPU memory, but very expensive pixels, since for every one we need to perform this round trip to main memory. These memory accesses are very expensive. Also consider that depending on the triangle being shaded, we might be accessing a very different section of the frame buffer, scattered all over, making it very difficult to take advantage of the cache. Desktops can easily cope with this, but it will not be feasible on mobile. On mobile devices, we typically find a tile-based renderer architecture. Focusing on the fragment processing, we are breaking down the shading into small tiles, for example 16 by 16 pixels on Mali, so that we can keep the working set in a small RAM coupled within the GPU. and then we write the tile back only to when the processing has been completed. To make this work, we need to know that all the triangles that are going to be present in each tile. So we need to divide the pipeline into two stages. The first processes all the geometry and creates a map so that we can know which triangles need to be processed by which tiles. This then needs to be stored in main memory. The second stage goes tile by tile, fetching the relevant triangle list and producing the final shaded pixels. The tile run means that we can keep all the data we need on chip during the pixel processing and only write out the final color at the very end. Some things might not even need to be written out at all, as we will see later. However, as you can see, we need to previously have written out all the geometry information beforehand. So in this case, we're trading more expensive triangles for less expensive pixels. And this is why we go for tile-based rendering on mobile. In summary, most mobile content is dominated by pixel cost. Mobile devices typically show high resolution, high frame rate, and the predominant use case are the user interface or many 2D games. So simple triangles, but lots of pixels and pixel blending. So in general, this is a trade-off that pays well. Tile-based renderers enable many optimizations that can save bandwidth and in turn power, which is what we need to provide the best user experience. Some of these optimizations are transparent to the user, but some require careful use of Vulkan to tell the GPU hardware all the information it needs to carry out these optimizations. First, we're going to discuss the goal of minimizing bandwidth. There are some Vulkan concepts that need to be well understood in order to write out the application in such a way that the tile-based renderer can take as much, can keep as much data as possible in the tile memory and avoid expensive accesses to main memory. One of these is Vulkan Renderpasses. Consider a simplified rendering pipeline for the sponsor scene. After geometry processing, the pixels are shaded using two attachments, color and depth. The collection of attachments and the way they're used is what is known in Vulkan as a render pass. Render passes, in turn, consist of one or more subpasses. When defining a render pass and its attachments, in Vulkan we need to specify load and store operations. That is, what to do with the attachments before and after each subpass. We define this for each attachment. This encapsulation allows the application to communicate the high-level frame graph to the driver. Tile-based GPUs can use this information to determine when to bring data on and off chip, and optimize out memory flashes or even discard some content of the tile buffers. When processing multiple subpasses, fragment shader invocations may access the data produced by the previous subpasses at the same pixel. Therefore, for each subpass, we will need to specify what to do with the attachments when the subpass begins, for example, clear it or restore it from memory, and what to do with the pixel data when the subpass ends, store it back to main memory or throw it away. The tile GPU can then know exactly when it needs to clear the tile memory, flash it, or restore it. Consider, for instance, the simple sponsor scene rendering. Once we're done determining the color of the pixels and present them on the screen, we do no longer need the depth information for the frame. We can then make sure that the depth information for each tile remains on chip and is discarded when writing out the color. In this simple example, we have saved a considerable amount of memory accesses, which will save power and in turn improve the user experience. Our advice is then to try maximizing the use of load up clear and store up don't care. This will not always be possible, depends on the content, but in many cases it can help make sure that we do not unnecessarily read or write to main memory. Additionally, for cases like the depth buffer that we just described, it is possible to tag the attachment as transient. This means that since it will not be coming from main memory and will not be needed after the shading is complete, the attachment does not need to have any space allocated for it in main memory. There are many other possible use cases for this, such as multi-sample attachments, which can be used to reduce aliasing but do not need to be written out to main memory, and in deferred pipelines, where the intermediate contents of the gbuffer may also be discarded once we have determined the final color of the pixels. I recommend you read our blog on deferred rendering on mobile, which goes into a bit more detail on this. We are now going to move on to pipeline bubbles. To get the best performance, the graphics stack aims to process multiple render passes in parallel, one being built on the CPU, one being vertex shaded, and one being fragment shaded. This overlapping of workloads ensures that the available processing units are kept busy all of the time. In Vulkan, managing execution dependencies between GPU commands is a responsibility of the application. These dependencies need to be strict enough to ensure correct rendering, but not so strict that they prevent parallelism. To specify these dependencies in Vulkan, we can use pipeline barriers. Barriers split the command stream in two parts. We will then specify at which destination stage in the graphics pipeline should the new commands wait, until all commands before the barrier have reached a certain source stage. The key here is to try and set up the source stage as early as possible in the pipeline, and the destination stage as late as possible. This will unblock as many stages as possible and improve performance. Hopefully this will become clearer with an example. Let's say that in our application, each render pass fragment shading needs the output of the previous render pass. In this case, we will keep the application safe and make sure that render passes are executed in order by inserting pipeline barriers between them and setting bottom to top dependencies. This means that all commands for a given render pass need to wait at the top of the pipeline, that is, to not run any stages, until all commands from the previous render pass have reached the very bottom or end of the pipeline. This is safe as we're ensuring that the dependencies are considered and we have no corruption in the color output. However, you can see that this is very inefficient as the GPU work slots are being kept idle, and this is what we refer to as bubbles in the pipeline. In contrast, see how we can remove these bubbles by specifying a more fine-grained barrier. Here, we're saying that commands for the second render pass need only to wait at the fragment processing stage until the result of the previous one has completed to ensure the correct rendering. This means that the vertex work for one render pass can proceed in parallel to the fragment work from the previous render pass, unblocking all the stages in between and achieving the parallelization that we wanted to aim for. So in general, the best practice here is to understand the dependencies and make sure that we avoid over-synchronization. If this did not make sense straight away, do not worry. Synchronization is probably the most complex area of Vulkan and takes time to grasp. Fortunately, there are many resources available to make it easier to understand and to get right. I wanted to briefly mention that the API has recently been updated with the new extension VKKHR Synchronization 2, which reorganizes some of the structs to make the API easier to understand. It is backwards compatible, and there is a lightweight emulation layer to assist in migrating to the new API. There is also a synchronization validation layer object, which can be enabled to trigger warnings and error messages about missing synchronization, which can also provide useful clues when debugging. Finally, here there are some blogs and guides that I found really helpful for understanding the topic in detail. Speaking of learning resources, I want to close today's presentation with a brief tour of this, and will encourage you to check them out when you have the chance, particularly if you're interested in learning more about Vulkan. I will start with Vulkan's new website, vulkan.org, which is updated regularly and serves as a hub for everything Vulkan. No matter what sort of background or target platform or application, there is something for everyone. I particularly highlight their code samples, which I will come back to later, and also Chronos' new YouTube channel dedicated to Vulkan. It includes many talks from conferences such as GDC and SIGGRAPH that go in detail on a wide range of topics. I also recommend checking out ARM's API guides for OpenGLES and Vulkan. Here we go in detail through the two examples that I covered, and many more. There is also a guide for everyone. We have a guide with best practices for game artists, covering things like geometry. For instance, we recommend always using level of detail in models. And texture best practices, covering compression and min-maps. Min-maps are one of those rare cases where we will get both better visual output as well as better performance. So there is really no reason not to use them. There are also guides that we have tailored for game engine users and game engine developers. All of this is available at developer.arm.com/graphics. While on the topic of best practices, I also wanted to point out Chronos best practice object, which, like the synchronization object that we mentioned earlier, is also included in the standard Chronos validation layer. Once enabled, it will emit warning messages, including advice on changes that, as an application developer, you can make to make sure that you are using tile-based hardware to optimal use, even if you do not have access to such a device. I also recommend the talk that LunarG recently delivered at SIGGRAPH, which goes in detail into examples of how to use this layer. There are more freely available and useful tools than ever before to develop for mobile. Here are just a few. RenderDoc will allow you to inspect all the API calls and verify that the pipeline values and RenderPass settings are what you expect. It can also process validation layer output and link it to the relevant RenderPasses and objects, so it's easier to find where in the pipeline you need to start debugging. For hardware counters and pipeline bubbles, you may also use Android GPU Inspector, which on supported devices will display a timeline of the RenderPass workloads, which make it easier to check for overlaps. Arm Mobile Studio is a complete package with a tool for each stage in the development workflow. It is particularly designed for mobile developers and can run with non-rooted devices. It can be used for CPU and GPU performance profiling, and for instance, the GPU active cycles in the fragment and non-fragment slots can also be inspected with Streamline, and this way you can check for pipeline bubbles that we mentioned earlier, alongside many other performance counters that provide good visibility of the whole system. All of this information can be overwhelming. So we have just released a set of video tutorials that will take you step by step through all the topics that we have covered today, from GPU macro architecture to API best practices, and finally, guides to using all the available tools to optimize your content. Last but not least, I'd like to point you to an invaluable resource that we have also been contributing to in the recent years, and that is Chronos Vulkan Samples repository on GitHub. This is a collection of open source runnable code that pull all of this theory into practice. They will allow you to run dedicated content with toggles so that you can measure for yourself the impact that the best practice recommendations have in the hardware. On ARM devices, you don't even need additional tools. The samples provide a mechanism to query and display the performance counters live on the device. It is also a suitable framework to start experimenting with Vulkan or to use it as a sandbox to research graphics techniques. You can load your own GLTF scenes. It is a very active community, with new samples being constantly added. For instance, recently, new samples illustrate extensions such as descriptor indexing, which have been available on desktop, and now we're also supporting on Mali. But note that these are contributed by many vendors, not just ARM. So the best practices showcased in the samples generally apply everywhere. Like the new 16-bit arithmetic sample, which showcases some performance and bandwidth optimizations that are valid for mobile as well as desktop GPUs. These are all the samples that are available today. They are divided into three main categories. API samples, which highlight the new Vulkan features and show you how to use them correctly. Extension samples, which similarly focus on newly released extensions and how to integrate them. And finally, performance samples, which focus on particular best practice recommendations from the many guides that I have shared earlier. This way, each sample showcases a particular scenario where the best practice recommendation is the bottleneck, so that you can switch in real time between the bad practice and the good practice and measure the impact that it has. And also note that many of these include a full tutorial or an article that not only documents the sample, but also dives into the theory behind it and contains links to further resources. Therefore, I encourage you to check them out when you have the chance. Here, I highlighted the ones that are particularly relevant to the talk today. The load store operation sample, as well as the MSAA and the subpass samples, dive deeper into the topic of render passes and memory bandwidth. And the pipeline various sample illustrates the effect of non-optimal synchronization. I hope that this will help you understand Vulkan and integrate the best practices into your games. And of course, you are all welcome to contribute and participate over at GitHub, even if just to suggest new samples that you'd be interested in. And this is all I wish to cover. I hope it proves useful. Thank you very much for listening.